So as we continue from the previous class that we had working on the basic view of our heat, I introduced and talked about the volumetric change of solids that we are going to be actually dealing with into consideration. And with that, we refer to the coefficients of expansion of solids. And the first part that we're going to consider under those coefficients of expansion is the one that affects on a linear change. The one that affects on a linear change. And which coefficient is that? That is the coefficient of linear expansion. So we're going to be talking about the coefficient of linear expansion. The coefficient of linear expansion, which is referred as alpha, all right? So that's alpha, which is, remember our Greek letter alpha, guys, in our mathematics. So that is the one that we are going to use to represent the linear change. For a coefficient of linear change, we are talking about a linear dimensional change. I want us to understand from this, if we have it like this, linear dimensional change, meaning to say the dimensions that we talk about that are under linear, which are going to be affected by the coefficient. They will be affected by the coefficient of linear expansion, which is alpha. Which linear dimensions are we talking about before we consider that coefficient of linear expansion? Which linear dimensions? We talk about the length, all right? We talk about the width. We talk about the height. Is it the height? Is it the diameter? Is it the radius? All these units, the basic units, guys, that you just take as they are. If it is meters, centimeters, millimeters, all right? There is no square unit there or cubic unit there. Those are linear. The unit, it's centimeters, not raised to any power, it's just centimeters. If it is meters, it's just meters. Those are linear dimensions that we're talking about. So anything that has got length, I mean, anything where we have got length, that's a linear. Where there's width, that's linear. Where there's height, it's linear. Diameter, remember diameter, if you talk about diameter of a circle, diameter of this, it's either meters, centimeters, millimeters. Same with radius. You can't say the radius of a circle is 2 square meters. No. The units of the radius, it's a linear, 2 meters. It's a linear dimension. So those ones that are under linear, they work with linear expansion, which is their coefficient, is called the coefficient of linear expansion. This is what I'm trying to say. So with this part, the coefficient of linear expansion, which is our alpha, the one that we are going to use, is simply the change in length. All right, let me write it down. This one, it is the change, all right, is the change in the length. All right, let me just say it like this. This one, simply the change in the length. All right, the change in the length of a material by 1 unit per unit change in temperature. Per unit change in temperature. This is the coefficient of linear expansion. So it is taken, or it is measured in per degree Celsius or per Kelvin. Per degree Celsius or per Kelvin. All right, whatever value that you are given here times 10 to the exponent per. degrees Celsius or per Kelvin. That is the coefficient of linear change, which is used on the what? On the expansion of linear dimensions as solids. These ones, it depends on the nature of the solid, the coefficient of linear of expansion. It depends on the nature of the solid, meaning to say it is not the same. Alpha, this one, the coefficient of linear of expansion is not the same. You are given for a certain solid, another solid has got its own. It depends on the nature of what? Of solid. So let us just have a point on that one. It depends on the nature. It depends on the nature of what? Of solid. So that's it. Let us quickly go to the calculations that can be done under a linear change. Under those linear dimensions, we are given a certain solid that is having an original length as it is like this. It will be having its original length at a given temperature. Let's say we have got LO, which is the original length, at a given temperature, T1, which is the original temperature. The material or the solid that we are given here, when it is subjected to a heat, when the temperature changes to T2, we are going to notice a change in length. Whether it is going to have a decrease because we are saying due to the change in length, it can be cooling down. The length can decrease or the length can increase, where we can see the change in length from what we had. We are going to notice the change in length. So here we are going to have the change in length. The change in length, that is the increment, the increase in length. By how much the length increased, by how much, or a decrease when it is going this side, when you're cooling down, there will be a decrease. So it can be an increase or a decrease in length. That is the change in length. So you're going to notice that the whole of this part now combined together will be our final length. Remember, the change in length occurred due to the change in temperature. All right, the change in length, let me write it here. The change in length occurred. The change, let me write in short. The change in length occurred due to what? Due to the change in temperature. That is the idea there. The change in length is affected by the change in temperature. So when that change occurs, the sum of these two, the original and that change that happened, gives us the final length, which is the length at T2 at the final temperature. Are we together there? So if we take this into consideration before we have our formulas, we are going to notice something. Original length is at the initial temperature, at original temperature. The original temperature is at T1, all right? The change in length is happening when there is a change in temperature. The final length is there when we are at the final temperature. It is at T2. Once you understand this, you are done. The change in length occurred due to the change in temperature. This is the one that we're going to have here. So this is it. So this is it, guys. It occurs at T1, it occurs when there's a change in temperature, occurs at T2. All right. So let's go back to the calculations that you're going to need. Then I think it's going to help us. So as for the calculations, guys, without wasting much time, do not worry about this. the final length, let's start with the final length. We can see that the final length that we are seeing here, so LF is the final length, I'm going to write them down, is the sum of these two mathematically, guys, by just saying it's what? Original plus the change in length. So the change in length, therefore, we can have it as change of subject here. So therefore, we can make original length. Maybe you're not given, you are given something. You can make whatever that you want. You can even make the change in the length of the subject by taking the original length to the other side. So it's going to be the final length minus the original length. That is the change in length, the increase in length or the decrease, depending with the condition that you're given. So what is or what must be calculated is the change in length at that change of temperature. So this one can be determined by the formula. The change in length is equal to, we are dealing with length, guys. Length is measured in what? Meters, centimeters, millimeters. That's linear. Length is linear. This one is linear. So you use the coefficient of linear, as we described before. We use the coefficient of linear expansion, which is what? Which is alpha. That is the one that you use. So the formula states that it is going to be alpha times the original length. Because this one is affected by what? The change in temperature. We must multiply to the change in temperature. So this is the formula that we are going to need, where the change in temperature is simply the difference between T2 and what? T1, guys, final minus what? Initial. The final minus initial, final minus original. So that is the idea that we are done. So this is it, guys. Guys, there's nothing. This one is going to be extended later on. You're just extending, multiplying by 2, multiplying by 3. They bring questions out of that. Then they say, it is not even difficult, guys. It is easy. It's not easy, but it's understandable. All right. So the alpha, as we explained here, represents our linear. Remember, this is the linear coefficient of expansion, all right, which is taken as per degree Celsius or per what? Or per Kelvin. We also have LO, that is the original length, the initial length of the object. So it represents the original length, which is the initial length of the object. So it can be in meters, it can be in millimeters, it can be in centimeters, depending with what you're working with, guys. On that person, you can use the units that you are comfortable with. So basically, we just use meters, but you can work with N1. And remember, we say the original length, it occurs where? It occurs at T1. So whenever we talk of the original length, we are talking about that length which is at T1. All right? We also have LF, which is the final length. So that's the final length. The length that you are given at T2, that one is your final length. The length that you are given at T2, all right? Then we talked about this one, which is actually the one that we are talking about here, the change in what? The change in length. So this one is simply the change in what? The change in length, which can be calculated from the formula or can be calculated when we know the final length and the original length. We simply have to find the difference. That's the change in length, or the increase or decrease. Increase or decrease in length. That's it. So it is just going to be same units, guys. If you are using millimeters, therefore it's going to be millimeters. That is the idea there, okay? Another thing that we have is the temperature. So the change in temperature, this one, it is the change in temperature, which I say T2 minus T1, final minus initial. So this one is the change in temperature. So it can also be an increase or a decrease. All right. And this change in temperature, as we can see, our linear coefficient of expansion can be taken as per degree Celsius. So our temperature can be measured in degrees Celsius or in Kelvin, as this one can also be per Kelvin. That is the idea. Remember, we talked about conversion to the Kelvin. We add 273. But guys, it's not necessary. We're going to talk about that in the examples. So T2 is the final, T1 is the initial. I think, yeah, that's it. Like I said, any change in temperature, in length, that change simply means we are talking about an increase or a decrease. So they can tell us a decrease in length, a decrease in temperature, an increase in temperature. That is the change in temperature. It is the change that we are given there. All right. So that is the one that we are having. So the change in length, this one, we cannot say at the change in temperature, but we say it corresponds with what? The change in temperature, just like original length corresponds with T1, this one with T2, so this one with the change in temperature. So that is it. So linear length. You're talking about length of an object, the width, radius, is it the diameter? Any linear dimension that you are given is affected by these formulas that we just had on this part. So these are the typical questions that we might be given on this section. The first question that we are given is the temperature of a 1.8 meter long stainless steel round bar. All right, no problem, guys. It's a round bar that you are given, this and that. What is important is the length. They are talking about how long, the unit, meters. This one is what? It's linear. You are dealing with a linear unit. What are you given there? Is the length. Length is in meters like this, 1.8 meters. That's a linear. So they are saying the temperature of a 1.8 long stainless steel, meaning to say the length of it is the original that you're given. That is the original value that you're given. Okay, but let's see what is happening. They say increases by. Guys, the English part also is important. It is not that much. Me, I'm not good at English. You understand me very well. I'm into mathematics. So, but some of these things, let's be mindful when we are reading. Increases by, then there is this one, increases to. Increases to 100 degrees Celsius. Increases to, it means we are now at that value. We are now at the final temperature T2. But if we say it increases by, that by is our increment. The increment, the change in temperature, the increase in temperature, what was increased from T1 to give us T2. We took the T1 and we added a change in temperature, then we got the T2. So it was increased by. That's the change in temperature there. They already gave us the change in temperature. Read your questions properly. Otherwise, you answer wrongly your questions. You answer wrongly your questions by not understanding your information. So they gave us the increment, the change in temperature. But since they mentioned that it increases, we know that the change in temperature that we are given, it's an increase. They told us it increases. They can say it decreases by. You know that it's a negative when it is like that. All right? When it is mentioned on a lathe, If the coefficient of linear expansion is given 19 times 10 to the exponent of -6, we know that per what? Per degree Celsius. Calculate. Let's go again to the question. Calculate the increase in length. What are they talking about? They have already mentioned something about what you are to calculate. What you are to calculate is the change in length. But they mentioned that that change in length is an increase. Why? Because there's an increase in temperature. So definitely the temperature, the length will increase. So the increase here in temperature that they are talking about, it is simply the change in length. And the final length of the bar, then the final length at the end. So the first thing, calculate the change in length, then the final length. You're done. You're done. We cannot talk about this formula because we need the final length. We cannot talk about that formula. So we are going to the basic formula, the change in length that we are given, that we said. All right, so let us just take here. So the first one, let's find the change in length. So we saw that the change in length under a linear dimension length. So you're going to use the coefficient of linear expansion times the original length times the change in temperature. Remember, change in temperature, T2 minus T1. So let us substitute. We've got everything there. 19 times 10 to the exponent of -6, the original length being 1,8 in what? In meters. The units here will also be for the change in length times the change in temperature. You're going to say T2 minus T1. No, we already have that change in length. So that's 30. Just like that. We already have the change in temperature, I mean. So we are going to have the change in length. That change in length is our increase. So if you were to simplify this, I want us to be careful on our calculator, guys. I have somehow explained on the calculator part, so I do not want to explain much here because your answers, just write the answers that you write your answers the way that you understand you as an individual. That I think that will be best. But as for me, let me put it here so that let me just show you something that is happening with this answer. If we are to simplify, it was 19 times 10 to the exponent of -6 times 1,8 times 30, like this. So that was going to give us this value. As you can see, guys, 0,001. We can write it, but we can even write it as times 10 to the exponent of -3, because we understand that times 10 to the exponent of -3, it is simply millimeters. Millimeters, milli means times 10 to the exponent of -3. So if we can write our answer as times 10 to the exponent of -3, or to convert to millimeters, it is easier. So how do I convert to millimeters? Remember, I told you guys, you multiply by the opposite of what you're converting to. You want to convert to this one, which is the millimeters. So you multiply by the opposite, 10 to the exponent of 3. Your answer as it is on your calculator, this one. Multiply it by 10 to the exponent of 3 like this. We are going to get 1,026. 1,026. Since we multiplied by this, it means our answer can be written as times 10 to the exponent of -3 in meters. Remember, this one simply means what? Milli, milli, milli. So that's a milli there. You guys, okay, let me put it this way. To convert to a certain unit, you multiply by the opposite. 10 to the exponent of 3, because we want to have 10 to the exponent of -3 on our answer. So we multiply by the opposite. That is the idea there. Okay, so anyways, this simply means a milli. So that's 1,026 millimeters. Or you can just even write it as it is like that. So you've got the change in what? the change in length. But the question is not ending there. They need you also to have the final length of the bar. So the final length, since we have the change in length and also the original length, it can be determined. Remember from our notes, we said final length is original plus the change in length. These to be added must be under same units. Same units. If you're using meters, let it be meters. If you're using centimeters, if you're using millimeters, let it be under same units. So the original length is in meters, 1,8 in meters. So I must use the change in length or that increase in length in meters also. Remember, this is our answer in meters, or just convert times 10 to the exponent of what? Minus 3. 1,026, sorry, times 10 to the exponent of minus 3 like this in meters. So that was going to give us the final length. So you're going to get 1,801, and so on and so on. So that's 1,801 in what? In meters. The final length. You play around the question. Play around with the information, guys. Understand your information. The information is there, but how to use it? Use it properly. Another question, using the same information, they are giving us a condition whereby we've got two rods. There are two rods, one aluminum and the other one steel, are 5 meters long. So the two rods, their original length is the same. The aluminum, the steel, they have the same length, originally being 5 meters. At this temperature, which is, remember, original temperature occurs at the initial or original, the original length occurs at the original temperature or the initial temperature. So we are given as 492 Kelvin. Don't worry about conversion, guys. Remember here it's given per Kelvin. So you can use your temperature as Kelvin. I said also that on our temperatures on the, all right, here, I think I mentioned here, temperatures. Degree Celsius or Kelvin. This one per Kelvin or per degree Celsius or per Kelvin. So you can use any consideration. If you want to convert, guys, there's no need for you to convert there. All right. Then the question was, calculate the length. Calculate the length. There are two of them there. At a temperature of 280. The temperature has changed from this one. It is now T2 at 280 Kelvin. And as we can see, that's a decrease from 492 to 280. That's a decrease, as we can see. We can see that one. It's a decrease. So meaning to say, when there's a decrease, we are going to have the length decreasing also. Okay, no problem about that. Let's focus on the question. The question is, calculate the length at this temperature, the length at T2. Which length do you call at T2? At T2, that's our final length at T2. Calculate the length at this step. This is the second one. So this is the final length. At T2, the length that operates there is what? The final length, or you can call it L2 if you want to use L2, depending with your understanding. That's the final length. That's our final length. So the question is simply needs us to calculate the final length. But remember, there are two rods. There are two materials that we are dealing, 2 metals. One aluminum, another one is steel. So we are going to calculate the final length for each. So let's start with steel. All right, so for steel, the final length formula, guys, does not change. The final length is still the same thing, original length plus the change in length. So we will need the change in length first for steel. So what is the change in length? Remember, the two, they use the original length. What is separate or what differs is their linear expansion. The coefficient of linear expansion is the one that differs, because we say it depends on the nature of solid. So for a steel, that's why we're given this one. That is the only thing that is going to change. So that's times the original length times the change in temperature. We have got the change in length for steel. All right, so taking our coefficient, the 12 times 10 to the exponent of -6 times the original length for both, they are fixed at 5 meters. Both, it is the same, times the change in length. Remember, that's T2 minus T1. We've got T2, we've got T1. T2 minus T1. Our T2 is given as what? 280 minus T1, which is 492. According to the proper formula, this is how you're supposed to have it. So it was going to give us a negative. The negative that we are seeing, it is to show us that there's a decrease. And as I was explaining, to say, guys, the temperature decreased there. That's why you get a negative on your answer, and it was going to be, all right, so that was going to give us negative 0.01 272, something like that, in meters. Since we used the original length here in meters, the change in length will be also in what? In meters. So we obtained the change in length for what? For steel. So therefore, its final length can be determined with that formula is for every linear, for every change, guys, that is going to happen. As long there is a change, the final length is always original plus the change that happened. So our original is the one that we're given before, guys. That is 5 plus. Remember, our change in length is a negative, meaning to say it's a decrease. So that's negative 0.012. All right, I was just supposed to round off here, no problem. Let me just save it. So it was going to give us something like 4,98728, something like that, which is 4,987 in meters, since we are working with the meters. So that is our final length for what? For steel. You are working with what? Steel, working with its linear coefficient of expansion. So the same thing was going to happen for aluminum to have its final length. To have its final length, you are going to need what is of aluminum. The linear coefficient is the one that is important. Is the one that is important. So for aluminum, it means we're going to need the change in length for our aluminum. Meaning to say this one is for aluminum, the linear coefficient of expansion. We are going to need for aluminum, just like that. So we already have it. 24 times 10 to the exponent of -6. Original length, like I said, these two, they are at what? 5 meters both. Then the change in length, as we saw, guys, T2 minus T1, that was 280 minus 492, just like that. So final minus initial. So we're going to get a negative value because of that decrease that we are seeing in temperature. So that was going to give us the change in length for aluminum of negative 0.02544 in meters, as we used this one in what? In meters. So same units. So therefore, we can calculate the final length for aluminum. So therefore, the final length for aluminum was going to be from the original length plus the change in length that we obtained for aluminum. All right. So the original length, guys, is still the 5 meters. The change in length, we got a negative value, negative 0.025. All right, I was just supposed to round off even on this one, but no problem. So that's 4,975 meters at the end. So that is how you play around with these typical questions, you just need to understand the basics of how the question is given. Work with the information, as you can see. It can be just like this. All right, let's quickly look into another one. We are given that on this question, which is example 3, a bar is 1.029 meters long at a temperature of, at this temperature, a certain bar is, so that's original length. The original length, 1.029 meters at this temperature at T1, 285 Kelvin. And this meters 8 from T1, where are we going? We are going to T2. So at T2, what length, which length do you use? At T2, the length is the final one. Once you understand that, you're done. The length that operates here is the final length. So the length they are giving you is the final length. They gave you the final length, 1.034 meters. And the question was, calculate the value of the coefficient of linear expansion. Calculate alpha. Calculate alpha from there. All right. From what we had on our notes, we can also make alpha the subject of the formula. I just want you to see this. From this part that we had before, we can make alpha the subject. Remember, we've got original length, change in length. We can also make change of subject, just make change of subject here. This alpha, the linear coefficient of expansion, can be written as what? We just have to divide it. So that's the change in length over what? The change in length over the original length times the change in temperature. But remember that the change in length can be determined from the final minus original length. This is the change in length. Final minus what? Original. So in place of that change in length, we can have it as final minus original over what? The original length into the change in temperature, T2 minus T1. Remember the change in temperature. This can be used. This can be used, guys. Change of subject. Be able to do that. Manipulate the formula to the way that you want, the way that you understand. So that's it. All right. So we saw that the change, our linear coefficient is equivalent to the change in length over what? The original length times the change in temperature. Yes, we can expand that formula. The original length is given by this and that. Then we substitute. No problem. Let's just write. No problem. No problem. We're going to write it. We're going to write it, guys. So do we have everything? That is the question. Do we have the final? The final is there. Original is there. T2. Okay, so this one, guys, was just a direct question, isn't it? It was just substituting into the formula. The final 1,034 minus same units. You must use same units. Original length is also in meters. 1.029 in meters. Everything over what? The original length. 1.029. Like this into the change in temperature as T2 minus T1, 370 minus 285. Take note, you are using the temperature in Kelvin. So your answer here, whatever that you're going to be having, must be per Kelvin. All right, so use per Kelvin on your answer. So let us simplify, guys, as we are to simplify. All right, we're going to get a value, guys, 0,0000, whatever that you have, 5, what is it? So the best unit that we can use as we have per Kelvin, we can have times 10 to the exponent of -6 per Kelvin. But I say to have that unit, what do? You multiply by the opposite. So on your answer that you're getting on your calculator, as it is multiply by 10 to the exponent of 6, the opposite of what? Minus 6. You are going to get 57. You are going to get 57,166 times what? The way you want to convert, you are converting to times 10 to the exponent of minus 6 per what? Per Kelvin. You want your answer to be written like this. So since we were using Kelvins here, this temperature was in Kelvin, this temperature was in Kelvin. Remember, they are under Kelvin, so also use per Kelvin. If you are given degrees Celsius, then also use per what? Per degree Celsius on your final answer. So that is how we play around these typical questions. Just try to add as many questions as you can, but we shall see as we move on. We still have a lot of sections under it that we just need to subdivide. It's not like too much. The whole topic is not that much, but we just have like a subsection, a subsection, a subsection. I'm just going to do those subsections. We combine them with question papers at the end of the day. But for now, that's it. That's it till we meet again.